the physics of semiconductor devices. In the last class, we spent quite a bit of time on trying to summarize the most important physics of semiconductors. We started talking about doping, understood what are band gaps, band edges, density of states, and one of the mechanisms by which we put carriers into the bands, electrons or holes, is by chemical doping, and we saw that we can change the resistivity of semiconductors over a very wide range by chemical doping, introducing extra electrons or making it electron rich by donors, for example with phosphorus in silicon, or electron poor or rich in holes by doping it with boron, for example, in silicon. So today what we're going to do is take that sort of picture that we developed and start putting together the most important building blocks of semiconductor devices. There are obviously a wide range of semiconductor devices. There are two-terminal devices like diodes and rectifiers and negative differential resistance devices, etc., oscillators. There are and then there are light-emitting diodes and lasers as well, which are two-terminal devices. And then there are devices that have electronic gain, which are typically three-terminal, bipolar transistors, field effect transistors, thyristors, etc. I mean, there are. So what we'll do today is take that idea of chemical doping, and in the very end of last class, we did end up drawing an energy band diagram, which looked like this, where I had one Fermi level and p-type semiconductor and an n-type semiconductor. Right? So, and we saw that if you put p and n regions next to each other, there's necessarily a bending of the bands. And that band bending, in the very end of the class, we calculated what is that band bending, and that's what's called the built-in voltage. And we found that that's essentially given by the thermal energy, kT, natural log of the doping densities on the two sides divided by the square of the intrinsic carrier density. So such relations are obviously very useful, because on the right side, you know everything. You know how much do you dope, what material you chose, so you know everything, so you can calculate this right away. And today what we're going to do is develop strategies for drawing a lot of the band diagrams and spend time trying to go into the details of what is the functional form of this, and look at various sorts of junctions. This is a p-n junction. We're going to look at what if I had n junction where the doping densities are different. So p-p junction. What if I had a semiconductor metal junction? What if I had two semiconductors with different band gaps? So those are all sorts of different junctions, and all of them help us in making devices of different kinds. So they are really the building blocks of many of the device technologies. The other thing I want to say is we discussed about putting carriers in the bands by doping, and there are many other ways. One of the most important another very important way of putting electrons into the conduction band or holes into the valence band is by electrostatic gating. So that's a gate of a field effect transistor. And we're going to actually, in the process of developing the tools for energy band diagrams, we're going to also develop the concept of what is a field effect, how do you put carriers in a band electrostatically. We're going to do it, this part I'm going to do in its full glory, meaning it will be completely quantum mechanical in the end. So we're going to do that, but actually it's very simple in the end. So I just want to kind of do that today. Okay, so what we want to start with today then, so this is kind of the summary of where we were in the last class. And we're going to now look at this sort of a junction in some detail, and we are going to look into electric fields, where are the charges, etc. And in that process, we're going to develop the idea of a band diagram. Now, one of the things I wanted to kind of cover before we get into the building blocks is once you put carriers in the bands, meaning I have lots of electrons in the conduction band here, lots of holes in the valence band here. I want to make sure we understand a couple of things. First is when I say I have an N-type semiconductor, I have electrons in the conduction band. So that's kind of the idea. And how many electrons I have far away from this junction, we saw that in general, I can always write N is a conduction band density of states. Right? We did that in the last class, times an exponential of E Fermi minus EC over KT. Right? So we wrote that in the last class. Right? How far is the Fermi level from the band edge? This is the band edge. Right? So let me. That's the electron density. Fermi level is this line, and that is the band edge. So you can see here, for example, the way it's drawn, EF minus EC is negative, right? So as a result, the electron density in the conduction band is less than the conduction band density. So that's pretty clear from here. If you dope it very heavily and you push the Fermi level into the band, it can be a little larger. So that's the number of electrons in the conduction band. Now here's the interesting question. How many holes do I have in the valence band in the N-type semiconductor? So how do I answer that question? Anybody help me with this? How many holes do I have here? Right, that's right. So the answer to that question is the following. Look, N times P in a semiconductor at equilibrium is always Ni squared. At equilibrium. Equilibrium, and what does that mean? And now equilibrium is a very interesting concept. So here you have made a PN junction and you just put it on the table. You don't apply any voltage, don't do anything to it. So then the whole device is in equilibrium. And you go very far into the N-type, this is always true. In fact, this is always true everywhere in the device, as long as you don't apply any voltage. And we'll see the moment you apply voltage, there's something else on the right side. We'll see that. So that's how you pull the stuff out of equilibrium, and then current starts flowing and that sort of thing. So, but at equilibrium, this is always true. Not just out here, also inside here, out here, everywhere. It's always true. As a result, the answer to the question is very straightforward. Now, very far on the right side, I don't have to do this actually. I can say that it is roughly equal to my doping density very far up on the right side, right? Because I've doped it, things have ionized, it's roughly that. As a result, the P, the hole density at this region, is Ni squared over the electron density, which is roughly equal to the doping density. Right? So even in an N-type semiconductor, I have a little bit of holes left. Right? So I would rather label it. Since I'm on the N side, typically I label it with a P sub N, saying this is the number of holes in the valence band in the N region. And as a result of this, let's look at some of the numbers. For example, let's say I have doped silicon at 10 to the power 17 per centimeter cube. Let's say I've doped it at 10 to the power 17 per centimeter cube. Then I know that Ni squared, Ni for silicon is 10 to the power 10, right? That we discussed or derived in the last class, right? 10 to the power 10 squared over 10 to the power 17. So how many holes do I have in my N-type semiconductor is roughly 10 to the power 3 per centimeter cube, right? So you can see that. So I have 10 to the power 17 per centimeter cube electrons and 10 to the power 3 per centimeter cube holes in an N-type semiconductor. So this is the reason why this would be called a minority carrier. Okay. A minority carrier, whereas electrons would be called the majority carriers in the. Makes sense? I mean, this the way that these are names attached to it, but and the reason why you have the minority carriers is again because of heat. Otherwise, there's no reason for it to exist. If you take the temperature away, you will get some. If you can degenerate dope it, and you can get rid of the holes, but you actually, if you dope it heavy enough, you won't be able to get rid of the electrons, for example. Right? So anyway, that's the difference, and you can see that the roles of majority and minority carriers switch as you go here. Right? Here you have much more holes, but very few electrons. Right? So, yeah. And when we look at any device that has a bipolar operation, meaning both electrons and holes matter, we'll see in all those devices the minority carrier plays the major role. It's very interesting, but it controls the entire operation of the device, like a p-n junction. The minority carrier will control all the operation of it. We'll see that, when we come to that. So even though it's called the minority carrier, it actually plays the major role in it. It's kind of the interesting concept. It's the wagging the dog sort of picture. It really plays a big role. Right? So, okay, so let me, is that clear? Any questions here? So even in an n-type semiconductor, I have some holes. Even in a p-type semiconductor, I have some electrons. They're just much smaller in number. So, and then they're called the minority carrier. Okay, so I'm going to actually now talk a little bit about after you put the carriers in the bands, how do you move them around? This is a very relatively short summary of what, again, actually next semester we're going to cover a whole course on it, which is on transport. Once you have electrons and holes in the bands, how do you move them around? Right? And that's obviously you apply some electric field or some other means. So, and this will be a quick summary. Okay? Because once we get into band diagrams, we will see why are we creating different heterostructures, because we want electrons or holes to move in a certain direction or in certain ways. So transport. Okay? And there are many levels of it, and as I mentioned just now, you can, there'll be a whole course next semester on it. But right now I'm going to summarize most of the semiconductor transport that we will need in this course in one equation. And then that's what's called the drift-diffusion equation. So I'm going to write J is the current density, and I'm going to show you some pictures of where it comes from. Let's say due to electrons, and there will be an equivalent equation for holes. This is the current density. And you can see very carefully that I'm not writing current, I'm writing current density, because as you can imagine, if you take a piece of semiconductor and you ask, a three-dimensional semiconductor, and you ask how much current is flowing, that's not a very illustrative question, because I can make the thing bigger or smaller, then the current doesn't have as much meaning as what is the density, which is essentially just the current divided by the area through which it's flowing, right? And that's for 3D. If you have 2 dimensions, you can really see in 3 dimensions, your current density will be in amps per, say, this is the unit we use, amps per centimeter square. Some mixed units, not quite SI. In 2D, typically what is used is amps, let me write it, milliamps. This is for, you can see that if you have 2 dimensions, you have just a line here. You don't have any area to flow through, you just have a width. So you have current per unit width. And these are, again, you can think of amps per meter, or this is typically what's used in transistors, milliamp per micron, because typically today transistors' widths are about a micron or so. The lengths are in 10 nanometers, but the width is about a micron. So, and in 1D, clearly you can see it's just amps. There's 1D, there's no basically in 1D means you have a dot through which you are flowing through. There's no width either. So depending on dimensions, I'm just writing the most general expression now, and unless otherwise I specify it, it's assumed it's 3 dimensions. It's assumed. Otherwise, if I specify, I'll specify if it's not. So in general, the current is always electron charge, which I'll represent with Q times the electron density times the velocity. So let's write the velocity as V. So that's one component of the current, which is, and there's another component of the current, which we will write as electron charge times a gradient in the electron density. Okay? Gradient in electron density. And this kind of already shows you that there's some sort of a diffusion going on. Electrons are flowing from larger density regions to smaller density regions. And there's a coefficient that represents how easy is that process, which is called the diffusion coefficient. So that's drift and diffusion. And even today, with the ballistic transistors and this and that, these two are still very important to understand device physics. Very, very important. So drift and diffusion. And that will be the heart of, for example, Schottky diodes, PN junctions, transistors, bipolar transistors that we're going to derive. So basically, in some regions of the device, this will dominate. In some other regions, this will dominate, and so on. And we'll realize that if I have a certain amount of current flowing into this material, into the semiconductor region here, exactly the same amount of current is going to come out here. Right? So current is continuous. That's current continuity, which is meaning if I can find the current at any plane across here, I'm done. That's the current everywhere. Right? Does it make sense? That's the current density everywhere. So that's also current continuity, which is also a very important quantity. Okay. So the drift, so this is the electron density, and you can ask, well, let's say I'm moving along this direction. This is my x direction, and at any point in some plane x, so this will be the density at that plane, right? So at the local density, and similarly, this will be the local velocity. And diffusion coefficients and all these things can change with x, is what I'm trying to say. Now, this n of x is clearly, as we have written already, if you know your, right, that's electron density. That's a connection to what we did in the last class. This is, based on density of states and all that sort of thing. Now, the velocity for drift, the microscopic picture is the electrons enter this solid, and then there might be lots of defects. And the electron goes, collides, goes some other way, collides with another defect. So, it's kind of moving in general to the right because there's an electric field or a force, let's say the force, that's due to the electric field that's trying to, in general, make it drift in that direction. But it's, it's as if it's basically you're throwing a ball in a forest and it will collide with the woods, but you have thrown it with certain force, so it will make it to a certain distance, yeah.
Is this formula, say, this also equilibrium condition or equilibrium condition?
Very good question. So the moment I apply an electric field, you're saying, is it in equilibrium? The answer is actually no. It's not valid in equilibrium if this is. But what we will do is we are going to actually build into this formalism. We're going to change our concept of Fermi level so as to make this formula always valid. And what we'll see that we are going to actually change this to what we call a quasi-Fermi level. The moment I pull it out of equilibrium, there is no one Fermi level in the material. So we are going to change it to the quasi-Fermi level. The moment you do that, this formula is still valid. So we're going to distort the concept of Fermi level to make this formula work, right? And okay, good point. Yeah. So the upshot of all this scattering and all these details with velocity is, in general, the velocity. If you experimentally plot the velocity, let me just So here's a sketch, or here's a figure. Sorry, it's not easily seen, but velocity as a function of electric field. So as you apply electric field, the velocity. So let me just label F as the field here. The velocity for small amounts of electric field is linearly proportional to the electric field, and that proportionality constant is called the mobility. So electron mobility or a hole mobility. That makes sense? So that's just a constant of proportionality. There are obviously a lot of microscopic details that go into it. If I have lots of defects, and if you have done some solid-state physics out of course, you will find that, it's related to the band structure, effective masses, scattering rates, and all that. That's where that goes in. The mobility is dependent on some microscopic details of the material and doping and defects and such things. But what you also notice is for some of the materials like silicon or germanium, as you increase the field, as you increase the electric field, at a certain point, the velocity starts saturating. For some of them, others, they show what's kind of a hump. We're not getting into those details here. In fact, there was a little question in the last class where I think Suren were asking what happens if you go into another valley. This is what happens when you go into another valley. You get negative differential resistance and that sort of thing. But right now, we're going to neglect that and say velocity initially increases linearly. When we say linear, if you have one order change in field, one order change in velocity, which is linear with power law with power of 1. and then it saturates, and that saturation is because the electrons are now scattering what you call inelastically. It is losing its energy. So it's a non-ohmic behavior. So this is the saturation of velocity. So the current will also saturate, and that was somewhat of a mystery in 1950s, because you imagine people have always measured current as a function of voltage, and metals it always is linear. And then suddenly they're measuring germanium and it starts saturating. It was like, why is it saturating? And then Shockley comes up with the idea that it is actually colliding with the lattice, setting of vibrations as a heating of the lattice. It's effectively Joule heating, but it is because of phonon scattering. Essentially, it loses its energy into the phonons and it collides with the lattice. Okay. The upshot of all that is instead of being linear at all fields, the velocity, we're going to take that into account with a very simple model. We're going to say that, well, I have something else in the denominator, and I think you can see this is, I'm going to just write it like that. So that captures the fact that if the field becomes very large, if f is very large, this is a characteristic saturation velocity. If f is very large, you can forget the 1, and then the mu f cancel, you get a saturation velocity. It just kind of gracefully goes from linearized to a saturation. Right? So that's a model for drift velocity as a function of electric field. Most of the times we can get away with just this low field, but in some cases we have to worry about the saturation as well. Okay, so that's the drift part. That's all I'm going to say, and there is some more details if you are interested. Maybe after the class or some other time I can discuss. The diffusion term is, as I was mentioning, is extremely important as well. And diffusion term. Actually, can you see, or there's some? Should I lower the screens a little more? Can you see clearly? Yeah. So the diffusion term is I think there's a picture I want to use, and I'm going to just give you a very quick summary of where you can think it comes from. Why is it like that? Why is it charged and diffusion constant times this dN by dx? So let's say this is x. And let's say we are moving along this, and for some reason I have a lot more electrons here, and then the electron density is going down for some reason. What might be the reason? Well, I might actually have an N and a P region here. So that's clearly a situation where the electron density will go down very fast, right? So I can plot that N as a function of x, and let's say it's kind of doing something like that. Right? So electron density, the function of x is changing, and you can ask, well, is there an effective current? And then you see, it's kind of the interesting question is I have no field in that region right now, at least, so no electric field. It's just that I have a lot more electrons here than here. This is just a density game now, right? And in principle, actually, if you look at the microscopic process, it's just a random walk, just a random walk process. This diffusion is very characteristic, and Einstein derived this for the first time. But you can see this, why would there be a net transport of carriers in a very simple way, that even if you don't have field, there are a lot more electrons here, and you look at this plane, and there are the carriers have some amount of thermal velocity. They're getting kicked around by the lattice, and the thermal velocity is roughly of the order of square root of kT by the effective mass. So kinetic energy is half mv squared. It's a factor of 2 and all that. But there's some amount of thermal velocity by which they're moving. If they're in 3D, they're moving in all three directions. And they, if I look at a plane, if I have, let's say this is, so I'm going to find out what is the current, in some sense, flowing in this region across this junction or this plane. And the point is, I also have electrons here, which are also moving with thermal velocities, but their number is just way smaller. So that's the difference. Okay. So if I look at it in this plane, there are exactly half of those are going to the right and half to the left. This is all in, I've now applied electric field. So you have that sort of microscopic reversibility. And similarly, half going to the right, half going to the left. So let's say, I want to find out what's the current at this point. Let's call that x. And we kind of call this as x plus lambda by 2. This point as x minus lambda by 2. And lambda is some sort of a mean-free path. And I'm not trying to go too deep into that right now. But if I ask what is the current here at this plane that's flowing to the right, or the current flowing to the right, that would be Q times the number of electrons at that plane. Right? The number of electrons at that plane is x plus lambda by 2, right? Number of electrons in the plane, times the velocity. Right? But the number of electrons that are moving to the right is half of that, not all. Right? So half of them is moving to the right, times the velocity is a thermal velocity. That's what you said. Does that make sense? So that's the number of electrons. This is not the total current. This is just the current, kind of the carriers going to the right here. And if you ask the question, where did they come from? Actually, those electrons, if the mean free path, if there's no scattering in between these 2 points, then they must have come from this plane. So that's the way to look at it, right? So it's the same as, so the current flowing is kind of the same as here. Similarly, the current flowing to the right, this plane is the same as here, and you write the total current, therefore, or in other words, what you can say that, let me put it this way. This is a mean free path, and what I'm going to ask is what's the current flowing here. So here what I'll do is total current flowing to the right minus total current flowing to the left. That's the right way to look at it. I think I probably led you in another direction. Let's look at it that way. On this plane, total flux going to the right minus total flux going to the left. Now total flux going to the left here is what I wrote here. Does this make sense? Because they came from here, right? And there's no scattering in between them. And the total flux going to the right here came from here, and so I have to subtract that, and I write it as minus Q x minus lambda by 2 over the thermal. Sorry?
Take your plus minus is flipped. You want to do this minus.
Right. I think I always make this little thing. And yeah, and these are actually so if there are electrons, this charge is also negative. So, I'm not going to get into that, but I think you understand what this is, okay? There's a question though, yeah.
When you say divided by 2, does it only work for one dimension, because in 3 dimension is spherical, right?
That's exactly right. So the dimensionality actually comes in as a factor here into the velocity itself. So I'm doing this in a more hand-wavy way, but you want to be precise, you must write that in 3 dimensions you have half m vx squared plus vy squared plus vz squared, right, is equal to, every dimension has half kt, so you have 3 by 2 kt, equipartition, and then so there's a little factors that I'm kind of skipping right now. There might be a pi if you do it even more accurately, so I'm skipping some of them right now. But yeah. So now, so as you can see I can now do a little bit of a change. So this is the current, and the sign you can fix, right? I mean, that if I have more electrons here, less electrons here, electrons will go that way, so the current is going that way. That's the idea, right? So yeah, so you can do a little bit of a manipulation here and write it as take out the V thermal and 2's and write n of x plus lambda by 2 minus n of x minus lambda by 2, and divide the whole thing by lambda, right, which is the mean free path, and multiply this by lambda here, right, and so you club these together, and you realize that what this is really is the derivative. This is the definition of a derivative, right, dn by dx, right, and in the limit of a very small lambda in the sense. So as a result, what we get is q times this combined unit here, which is the thermal velocity times the mean free path over 2 times dn over dx, and this thing is what is the heart of what's the diffusion coefficient. This is the definition of diffusion coefficient. So the velocity is in centimeters per second. Mean free path is centimeters, so you can see diffusion coefficient would have units of centimeters square over second, which is a strange unit, but that's what it is.
Yeah. The band diagram is flat, and there's no difference in n of x is constant.
Yeah.
And you have equilibrium with 0.
That's correct. That's exactly right. If the electron density is not changing, then there's no diffusion current. That is
And
correct.
it's just solely drift.
Then it can be drift if you apply a field. Yeah, if you apply an electric
If
field.
not, it's just all drift.
It is 0, yeah. And it is 0, but the net current is 0. So let's see. You're asking also a very important question which we will invoke. Exactly right. So when carrier density is like that, yes, the net current is 0, but still half is going that way, half is going that way. It's always balanced. Right? So, and whenever we make a junction, we actually break that balance. So there's always 0 current on the whole, but when you break the balance, you get a current. So, and it might seem here that the only way you can get this sort of diffusion is by heat. And that is true if you have semiconductors that are not doped very heavily. In fact, by this relation, as you kind of just mentioned, even if you create a gradient, as you can see that if I just create a gradient and I leave the material and don't apply a field, there will be some current flowing, but the current cannot flow forever. I mean, there's no external voltage, right? So what will happen is, if I have such a distribution and I have not applied an electric field, so I start with this sort of a distribution, and there'll be electron that will flow this way, right? And there'll be a little current flow, but that is not going to survive for too long, right? Why? Because as you lose electrons from here, this part starts getting slightly positively charged. This part starts getting slightly more negatively charged because electrons are moving that way, and you set up an electric field. Right? And that electric field opposes this motion, and at some point it's going to reach equilibrium. And when is that equilibrium? When these two terms become equal. Right? And when they become equal, you can equate mobility times field and all that. You get what's the Einstein relation. That diffusion coefficient by mobility is kT by q, or kT by electron charge. That's where it comes from. That the diffusion coefficient is related to the mobility by kT by q. The Einstein relation. So, okay, so it was a long detour, but that's all I'm going to say about transport now. And we're going to make use of it in the next lecture when we talk about Schottky diodes and PN junctions. We're going to make use of it heavily. But right now, what I want to do for the rest of the hour today is look at energy band diagrams and that sort of thing. So, but that's the transport summary for now. Okay. Yeah, please.
The current density equation, is that just, I'm sure there's a derivation of, like, how do you know those are the only two terms in that? Because not
yeah, that's a good point, yeah. So,
is it an exact equality, or is it a model?
When we look at the Schottky and the PN junction, and when we are when we'll start talk about currents, what we'll see is all these terms. There can be many other terms. If I take a piece of semiconductor, and this edge of the semiconductor, I don't apply any voltage. But what I do is I take these two regions, this end I attach it to a very hot object, this end is cold. You still have a current flow. That's called a thermoelectric effect. So there is no voltage difference, but there is a current flowing. So that there will be another term which is called the Seebeck coefficient and all that. So there are all these things that emerge. The most general relation is basically that current is a vector, is given by Q gradient of what you call as the quasi-Fermi level, and we'll see that when we work through the currents. And by just doing that, actually Q times the diffusion coefficient times this gradient of a quasi-Fermi level, and that is a representation that if you perturb the system, you apply some voltage or heat or light or something like that, you always change the Fermi level. And from there, all these terms emerge. So that's the heart of the problem, the way we understand transport, and we'll see that. So there's also light, photoconductivity. There's you can have current in many ways, right? So okay, so let's go towards energy band diagrams now, and the whole reason we are going to do all these band diagrams, different designs, is really to control the flow of current. And you control the flow of current just like you control many other things. You put barriers in the way of things, right? Because just like you want to control the speed of traffic, you can have some signals and all that. So it's a barrier in some sense, right? So in semiconductors, you have electrons and holes that want to move, And most of the times what you want to do is you want one of them to move, you don't want the other to move. And that's a very interesting problem, most of the times, for a useful device. And you want to control how, here's the energy band diagram of a semiconductor at equilibrium. When I apply a voltage across the PN junction, what happens is there will be electric field, and we're going to discuss this in some detail. And if I have bands which are filled with electrons, let's say I doped it, then the electrons can move, holes can move, and generally electrons would always want to go down in energy, and holes would want to go up in energy, just like bubbles and water. I think the good example is you have a tube and water, and you bend the tube. Water always goes to the bottom, and the air goes to the top. Right? That's the idea. Holes always go to because they energetically. That's their lowest energy state. That's all. Yeah. And if you want to look at the microscopic picture of this situation, is what you have is the energy band diagram looks like this, right? EV, EC. But really, what's going on is you have formed two contacts to these two regions, the two metal electrodes that are connected to the semiconductor. Okay? And the metal electrodes have energy levels that are filled up all the way to, let's say, if you have connected to the N-type, if it's an N-type semiconductor, you have electrons in the metal that are filled all the way to that level. That's the Fermi level of the metal. And then you have electrons that are already in the conduction band because you have doped it with donors. Right? You have pushed up some electrons into the band. And when I take two metals and I apply a voltage across them, right? Okay. Well, all I do is I actually change the levels of the highest occupied states of electrons between the two. The battery essentially just moves charges between the two. So ordinarily the two metals were the same, and when you apply a voltage, you just shift it by whatever voltage you apply across it. You just shift that energy level. And these are all, in some sense, quantum mechanical energy levels. Electrons in a metal are also undergoing all these block wave functions, this, that, but they have energies and they're continuous. There's no gap for the metal. And is this, let me just see whether I drew this correctly. So this is a situation where, how do I know whether I drew it correctly, whether, when I draw the battery like that, it looks like here's positive, here's negative. But I think this is not quite right, because you see electrons in this situation will stream down this way. They want to go this way. Why? Because deep in the semiconductor, this is a band. This is the band edge, EC. And above it, as we saw, there's a bunch of energies, right? This is a band. This is all these energies. And these are all energies allowed for the electron. And all that I'm doing by applying a voltage across this is, microscopically, if you look at all these planes, you have energy level here, energy level here, energy level. I mean, there are all, different. There's a lot of very dense set of energies that are in there now. And the electron enters from the metal, and then it says, oh, well, there's another energy lower, and it keeps going. It ends up here. But the moment it ends up here, the battery, as you can see, the electrons are moving this way. And you will never go wrong by thinking that electron always goes towards a positive electrode, and that's correct. Right? So clearly what I drew is not quite right, so it should be the other way around. It should be positive on this side. It's always correct. So electrons will always go towards the positive electrode, and this is what will happen when you apply a voltage. And microscopically, it's always the energy levels. So essentially what you're doing when you apply voltage is you are just playing around with what energy levels are occupied. But what we use as a very unifying concept in semiconductor physics is the concept of electric field. The electric field is a consequence. It's really not, the truth of the matter is there are all these energy levels. You can think of it completely in terms of energy and not even invoke electric field. You can think of it that way. In fact, as the devices get smaller and smaller, sometimes you run into a lot of trouble if you think about electric fields also. Sometimes. But this is the picture. So electrons stream down. So there's all these details, but again, we are not going to draw these details of the bands. We're just going to look at the band now. And similarly, if I had a hole here, that will keep going up. the way to look at that is if I have a hole that's an empty state, and you can see all these electron states above that are occupied, so an electron state will jump here, and the hole effectively moves here, right? And so on. So the hole is always popular. Okay, so now this is a uniform field, for example, where the bands bend uniformly, and you will get an ohmic contact then, meaning I versus V would be kind of linear. If you put a barrier like in a PN junction or a Schottky diode, you'll get rectifying current, and we're going to derive those things. And if you make a 3-terminal device, which is essentially very similar to the Schottky diode, but you kind of, this part, you flip it around, and you inject more and more carriers. You get a little bit of current, you get a more. You flip that around, that's a transistor. So it's a Schottky diode flipped around with a third terminal is a transistor. So it's a field effect transistor. So we're going to look at those things in some detail now. And let's look at first, we have only looked at doped semiconductors and intrinsic semiconductors, but there's a wider, richer range of things. And okay, so I think you probably are aware, the Nobel Prize in Physics in 2000 went to guys who, the integrated circuit, the CMOS logic circuits, and two people who made the semiconductor laser and bipolar transistors possible, and they won the award for the heterostructures. And what is a heterostructure? This is a very interesting concept in semiconductor physics. So the heart of the heterostructure is the following. Okay, so in a normal semiconductor, if you have n-type semiconductor like what we have here, you have electrons that will flow down, right? Because we think there's an electric field, electrons are negatively charged, and there's an electric field that points in that direction, so the electron gets pulled. There's a force on the electron in that direction, right? So it goes that way. In the same semiconductor, if I manage to create a hole, for the hole, the force is in the opposite direction. Right? So, and you can imagine that pretty much every time I have an electron, and I have a positive charge, right? So I have a negative charge and a positive charge, and I put both of them in a region which has some sort of electric field that's pointing to the right, right? And then the electron will always move this way, and the hole will always move that way. That's at least what Coulomb's law tells us, right? Coulomb force is going to pull them in another way. Right? But what these guys realized is actually in semiconductors, you can do something very weird. You can actually create a situation when both of them will move, so both of them will move in the same direction. It's very weird. You can create that situation. You can even create a situation when one of them will not move, the other will move. And that is the heart of a heterostructure. Okay? A heterostructure breaks this sort of a symmetry that Coulomb's law assumes by clever choice of materials. So by clever choice of materials. And here's a very simple example where you can see why this would happen. And this is actually really pretty much it in some sense. So you take a semiconductor which has the same band gap everywhere. And I just discussed if you have electron, it will go to the right. If you have a field like this, electron goes to the right, hole goes to the left. Okay. But now you create a semiconductor, and this we can create when we do material growth and all that sort of thing. I create a semiconductor where on this side, on the left side, I have a very large band gap, the left side. But on the right side, I have a very small band gap. I create such a semiconductor. So my energy band diagram here would look something like that. Make sense? So this is the valence band edge. This is the conduction band edge. Right? And this is my semiconductor now. I mean, this is the band gap, and the band gap is changing across this material. Does that make sense? I mean, so this is called a graded heterojunction semiconductor, and then these states are filled, these are empty. Now you can see that if I release an electron here, it will move to the right. But if I release a hole here, it's not going to do anything. So you have broken some sort of very intrinsic symmetry in the material, and you can flip this around. You can make it, not possible for electrons to move, whereas the holes can move, right? So this sort of a field, there's no external field in this material. Right? This field is born out of the atoms of the material itself. It's called a quasi-electric field. A quasi-electric field. Again, this is just a name, but it's saying that by careful choice of materials, you can create these built-in fields which are not because of an external battery, an external voltage. Right? So that's and then clearly you can see for that you need band gaps that are changing in space. You can create a situation like this where both electrons and holes are moving to the right, because the holes wants to be on the top of the valence band, electrons want to be at the bottom of the conductor. They're both moving to the right. And you can create, so clearly this situation is somewhat counterintuitive, but this is what semiconductor heterostructures do. And to create these structures, you need a large range of semiconductors with different band gaps and alignments and that sort of thing. So that article is kind of nice, you can read up. So we have a very wide range of semiconductors. You have silicon, germanium. You can see now the bands are such that silicon is here, germanium valence band is here, conduction band of germanium is here, conduction band of silicon is here. So if you mix them, if you create an abrupt junction between silicon and germanium, then it will look like this. So I have conduction band of silicon, valence band of silicon, and then germanium looks like this, right? So it has an abrupt junction EV. Right? You see that? So silicon, germanium. These are pure silicon and pure germanium. There's a little offset. So this is, and germanium has a smaller band gap, so maybe I should draw it a little more accurately. EV. This is how it looks. If you start with silicon and you kind of gradually go to germanium, which is silicon 100% silicon, and then you add 1% germanium, 2%, 3%, and then go to 100% germanium. It's called a graded junction. So what you'll get in between them is, the band gaps will kind of gradually go like that. Makes sense? That's a graded junction. So that's you change the composition as you grow the material. This sort of a silicon germanium alloy is now used in a MOSFET, which is in the CMOS transistors that we use today in the ohmic contact regions. They also, because of lattice mismatch, they also introduce strain and that sort of thing. So it's already used. And then you have other materials, nitrides and arsenides. There's a whole zoo of semiconductors. And so this sort of alignment we just saw, where the conduction band, is lined that way, valence bands are lined that way. This is called a type 2 sort of called a staggered heterojunction. This is a heterojunction between two materials. It's called type 2, where you can see it's a staggered thing. You can have a situation when I have the narrow band gap material is completely contained within the wider band gap material. You can have alignment that looks like that between two materials, and that would be a type 1 or a straddling. And finally, you can have a situation very strange, which is called a broken gap material, where so this is type 1, type 2, and type 3 is when the conduction band of the other second semiconductor is below the valence band edge of the first semiconductor. That's a very strange situation, but you can have that as well. Right? So that's type 3, broken gap material. And one of the very important broken gap materials is when you take gallium antimonide, GaSb, and indium arsenide. And you can see, the valence band kind of starts rising above the conduction band of that, or indium antimonide with indium arsenide. You can see their broken gap. So all of them have very important uses. So some transistors, some lasers, some other things. That's a question? Yeah.
So silicon germanium.
Yeah.
So if you draw the formula, it would be like.
Yeah, we are going to talk about that now, right? That's right. So now, ask a very interesting question. So where's the Fermi level? If you could just create a normal junction here, and let's look at an example of that, where instead of getting a sharp junction, let's look at a graded junction. Okay? So the Fermi level is very intimately tied to whether you are doping the material or not. So the doping, for example, if I take a graded material, which let's say looks something like that, okay? You can think of this as silicon and this is germanium, okay? And this is Seagate in between them. Right? You can think of it that way. And this is the valence band, that's the conduction band. Let's say I dope this whole region, the entire thickness of this layer with p-type. If I dope it with p-type and I kind of do a relatively uniform doping, what that will ensure is I have Na is the doping density will become equal to p, right? The whole density will be roughly equal to p, and that will be, in some sense, NV exponential of EV minus EF over KT, right? Does that make sense? So you can turn this around and say that my valence band edge will therefore be EF minus, KT, natural log, some details here, NA over NV, right? So how far is your Fermi level from the valence band edge. So you can draw the band diagram now. And I draw it. I have not done anything strange. I've not applied any electric field, so my Fermi level is always constant. And so what will happen now is the valence band will be this much distance away. You know what it is now. So it will look relatively flat, but I'm not trying to draw it exactly. There'll be a slight change because NV is changing with space a little bit. But that's minor. It's a logarithmic correction. It's very small. But what you see is that all the change actually appears in the conduction band. Make sense? So by doping, that's how you control how the band diagram really looks. So you dope it p-type, this is what happens. So the band diagram will look with conduction band here, valence band here. By doping, you fixed this. And you dope it n-type, as you can see, you'll switch it around. The conduction band will become flat, but the valence band will look like that.
So why is it when you dope something, when you apply electric field with two metal contacts, it doesn't change the band edge?
The band edge.
You're saying it's flat because it's doped, so like...
Oh, yeah. No, now if I apply an electric field, the whole thing will bend as well.
Okay.
No, it will. Yeah.
So then why is it bended now?
Okay, so that is because of the heterostructure. I mean, this is because this is exactly the essence of what we call as a quasi-electric field. This is not an external voltage. This is built into the material because you change from silicon to silicon germanium, and you doped it p-type. The combination of these two has created given birth to, in some sense, a built-in electric field in the material.
So doing a heterostructure is equivalent to putting two metal electrodes in a structure.
In a certain sense, it is similar. In a certain sense, and so I can go, do a lot more fun things. You can take a narrow gap material and put two wide gap materials of type 1 next to each other, and this is a quantum well now. You can thin it down very small, and you inject electrons, holes, and generally this is the heart of lasers and LEDs and that sort of thing. Quantum well design, and in fact, a lot of transistors today also use this. So electrons get trapped, holes get trapped because there are barriers around on both sides, and so you have a lot of room to play with these structures. Okay, good. And we will look at them in reasonable detail when the time comes for those particular devices. This sort of a behavior, this sort of a structure, where you have silicon germanium graded junctions, is currently used in a lot of mobile devices, in a bi-CMOS, where it's a bipolar transistor, but the base of the bipolar transistor is graded. It's a graded base. It's called a heterostructure bipolar transistor. Typically what happens, why do you grade it? What does it buy you? Is typically, if you don't grade it, you have a flat band here, and you inject a lot of electrons, and they have to kind of diffuse across. Diffusion is relatively slow. You build in this electric field, and the electrons get a huge boost in the speed, and the transistor speed goes up by quite a bit, actually. So this is called a Seagate HBT, heterostructure bipolar transistor. I think most of them are produced in the Fishkill facility not too far from here, in IBM, silicon germanium HBT technology, and then it reaches about 300 or 400 gigahertz now, very fast devices. And they make use of this quasi-electric field to speed up the device. Okay, so that's and then you obviously have metals, and you can see there are materials with aluminum nitride. It's a very wide band gap, 6 electron volts or so, typically called insulators. But if you can dope them, you can now make devices with it. So you can think of it also as a semiconductor. So very large range of gaps and all that sort of thing. Okay, so now with the range of materials and some of the transport, let's look at two building blocks of device physics, of band diagrams. Okay? So we will start, let's not worry about that right now. One of the things you can see is if I took a junction that looks, for example, instead of grading a band gap like that, you can take an abrupt junction like that, okay? Right? And let's say you create electrons here and holes here. They will not stay there, right? Why? Because there's a lower energy available there. So the electrons will end up here, holes will end up here. This is just another way of saying that there's some sort of a built-in quasi-electric field that's pushing both electrons and holes into the same direction. In a graded junction, it's easy to see, but in an abrupt junction, that happens much faster in some sense, right? And the field is like a very small window where the junction is. That's what the field is. This is like a delta function field. In that window, you have a huge field. It just kicks the electrons and holes into the same direction. Yeah. So that's a heterojunction capability. So what we're going to do now is start looking at how do we design the fields. There's doping, there is heterojunctions, band gaps, but we are going to design it, and we're going to look at it. So, and I think there's a famous statement by Kroma which says that if in discussing a semiconductor problem, you cannot draw an energy band diagram that shows that you don't know what you're talking about. And if you can draw one, but you don't draw, then the audience won't know what you're talking about. So there's good reason to learn it. And let's start by looking at one of the simplest problems, which will lead us to the energy band diagram, how to draw it. And the heart of band diagram is actually a very simple idea. It is an energy band diagram is how energy changes in space. Right? I mean, that's what it is. Right? How is energy changing in space? Now, energy is a potential in electrostatics. It is potential. Energy is charge times potential energy, right? V. And how does potential depend in space? And that answer, how do you find that? There's only one way to find that answer. How do you find the potential in space? 150 years ago, somebody gave us an equation, right? If I want to find the potential in space because of charges, in response to charges and things like that, how do I do that, right? The Poisson equation, right? Or basically Maxwell's equations, right? And that's where it boils down to. So if I just ask, well, Maxwell's equations, there are 4, but in energy band diagrams and electrostatics, let me just write down the Maxwell's, and then we'll see where and which ones are important where, right? So you get curls and divergences. The last 3 will, I'll just point out where they'll be important, and then we'll move along. Okay, so 4 Maxwell's equations. As you know, Maxwell really, this was his input, and then he kind of synthesized he unified all 4, electricity, magnetism. But this is something he came up with, right? So this is new. Before him, Gauss already knew this, Faraday knew this, and Ampere knew this. Right? So the Ampere's law, Faraday law, Gauss law, and all that stuff, right? But if we are looking at transistors in the time domain, meaning I'm doing a 300 gigahertz circuit or something like that, then I will be worried about these 2 terms. I would be worried about, not just worried about, I use this to design the device and design the structures and all that stuff. But right now, in band diagrams, we're going to look at only electrostatics. So all d by dt is 0 for us. So d by dt is 0. Electric and magnetic fields don't couple. And this term is also, we don't need it. Right now, we don't need it. And for electrostatics, this is all I need. That's all. And this is basically Gauss law, and I think you know that electric field is the negative gradient of the potential, right? Electric field is negative gradient of the potential, and that we are saying is charge over the dielectric constant. Charge density, rho, is the charge density in coulombs over volume density of charge. Net charge, it doesn't care about whether you're talking electrons or holes or donors, etc. It only wants the net charge, the total charge. Give me the final number. After all the positives and negatives have cancelled, what's left is what charge there is. And so this is, it has Poisson equation. This is the name of the equation, and then that's what we are really solving most of the time, and for energy band diagrams. And let me just conclude by saying that energy band diagram is a pictorial representation of the Poisson equation. It's a pictorial representation. That's all there is to it. We're drawing it, in space. We're drawing a picture of that. And it just so happens it's the pictorial representation in a semiconductor which has band gaps and that sort of thing. So band gaps, so things are changing, band edges, and that sort of thing. So so that's what we're going to solve. And I think you know the solutions to many problems already as far as solving the Poisson equation. In drawing energy band diagrams, we always want to start from locate the charge, because that's my source term. Right? Find the charge. Right? Where's the charge? Right? Once you find the charge, you can go through an intermediate process where I think you realize that is really your electric field, right? Okay. So you can find the field. Field gives you a little bit of intuition as well. So you go from charge to field, and then you go from field to potential, which is V of x, which is really your energy band diagram, right? Energy. So we go this way generally. Start with charge, locate where is the charge, right? And then go to the field and then find the energy band diagram. And to do that, I think the simplest one, which you have seen many, many times, is what is this process if I just had one point charge, right? Let's say I have charge Q, and I ask you, find me the potential around it and all that. So because of this point charge, what is the field, what is the energy, all that. Can I draw it? Where might this situation be? For example, I can take a semiconductor and I have an ionized donor, which is a phosphorus atom, for example, and have very few electrons, and then I have the whole crystal around it, which is all other atoms are silicon. So I have a positive charge that's sitting there and really nothing much around, right? Here's a situation where I want draw me the energy band diagram near that phosphorus atom or the donor atom, right? How will it look? Well, this problem we have solved, right? It's a 3D problem. Where 3D, there's 1 point charge, right? And what's the potential at any point, or what's the field at any point? We know that. Right? Potential at any point, a distance r, would be q over 4 pi epsilon, but you are in a semiconductor, so I would find the dielectric constant of the semiconductor times r, right? And that's your potential at a certain distance r. And then the field would go as r squared and all that, right? Inverse square law, right? So that is easy. And so if you want to draw the energy band diagram around here, if you go along that direction, there will be a little, so because of the positive charge, microscopically, if I draw the energy band diagram near here, so far away the bands are flat, but very near to that there's a little positive charge, and you won't go wrong in understanding that it will kind of do a little bit of thing like that, because it's going to pull electrons in, right? And the nature of that is 1 over r. Is 1 over r. Right? So I'm not getting into the detail of this. This is a microscopic thing, and there are free electrons, so they'll kind of crowd in, and then actually they will smoothen this out because of screening. I'm not getting into that right now. What I want to get into is a much more, instead of a point charge, what I want to get into is for most devices, one of the most important charge charge geometries that plays a big role in many devices is a sheet charge, a two-dimensional sheet charge. So here's another question. I have a sheet charge, 2 dimensions. Okay, so x, y. So let's say I have a positive sheet charge. There are positive charges here, and the sheet charge density is rho coulombs per centimeter square. This is the sheet charge density. How many positives per centimeter square? You can think of it as uniformly distributed. And so that's, let's say, x and y. And I'm sitting here at z. And I ask the question, well, tell me what's the field here? What's the field there? Now that's also, I think Gauss law gives you, if you have done this many times, I think you kind of do a little, I don't know what, like a pill box here, and go in and do your little box there, right? And you integrate, you do Gauss law in integral form because it has the symmetry. It allows you to do that. So sigma ds over epsilon. Right? So, does that make sense? I mean, this is how you get it, and I think you know that because of the positive charge, the electric field here is going to point out, electric field there is going to point that way, but the fields are exactly equal, and then things like that. So you get 2 times the electric field times pi r squared, where pi squared is the area, is equal to sheet density times pi r squared is the total enclosed charge here, right? And divided by the dielectric constant. And so the electric field due to a sheet charge is sigma by 2 epsilon. Right? So this is something you know, and let me put it this way. This is actually probably in energy band diagrams and other things, is one of the most important results. It's the simplest one, but it's very, very important. Right? So if you understand this, it will take you very, very far. Schottky diodes, PN junctions, bipolars, FETs will take you very far. It's a very simple relation, but what it's saying is, look, if I had a sheet charge, positive sheet charge, let's say, no matter how far I am from it, my field is always the same. The field is not changing. It's very weird if you think about it, but this is actually correct. And the field is the sheet charge density divided by twice dielectric constant, and it's pointing, if I have positive charge, it's pointing away from the sheet, and if I have negative charge, it's pointing towards the sheet. So that's all it's saying. And the other thing is it's useful to have a magnitude of this. So let's look at a magnitude. Just for memory, I would say that if you had a sheet charge which is of the order of 10 to the power 13 per centimeter square, these are numbers that will appear many times in semiconductor devices, PN junctions, MOSFETs. And the dielectric constant typically in a semiconductor is about 10, right? 10, 9, depends on what we are talking about, is 10 times epsilon naught. You can plug in the numbers, and what you will get, so there's a Q here, electron charge here, but this is the sheet density. So you will get, it's roughly 10 to the power 6 volts per centimeter. That's the field you will get. So 1 megavolt per centimeter. If you have 10 to the power 13 per centimeter square sheet charge density, very useful order of magnitude. So if you have 10 to the power 12, I have 10 to the power 5 volt, order of magnitude of fields. And again, I mean, this is obviously nothing very fancy. You can make a nice little plot of it. What happens is actually this sort of field, because you can change these charges by many orders of magnitude. So for 10 to the power 13, I'm talking about, sorry, it's hard to see, but it's about 10 to the power 6 volts per centimeter. 10 to the power 10, down here. And in a semiconductor, we can change the density of charges by many, many orders, which is why we can change the field by many, many orders. So yeah. And the field control is typically always like that, with sort of sheet charge density. Is that clear? I mean, this is, so as a result, if I have this sort of a field and I ask, what is the, now you told me I have a charge, and you gave me the field, so how should the energy band diagram look like? Let's try to draw it, right? So the question now is, I have a sheet charge that I have inserted into a piece of semiconductor. Insert a sheet charge into a piece of semiconductor. And then ask, draw me the energy band diagram around it, nearby it and all that. And I think you can see that if I have a positive sheet charge, if I have a positive sheet charge, that charge is going to attract electrons. So that already tells you which way the band is going to bend, at least. That should be immediately clear that the direction should. So what I'm saying is I take a piece of block of silicon and I insert a plane by ion implantation or growth or whatever, a sheet of positive charges here. And I ask, draw me the energy band diagram in that direction. So here's the genesis of how one would go around doing that, right? So I start by drawing my charge. And the charge is a sheet charge. It's sigma. That's good. It's a sheet charge in the x direction. So it's a kind of a, very sharply peaked delta. And then I draw the field for it. The field, we saw that on the right side, the field will be to the right. On the left side, it will be to the left. And the field magnitude on the right side is exactly equal to sigma by 2 times epsilon. Right? So we just calculated that. the field is pointing to the right, sigma by 2 epsilon. And at the interface here, it's going to switch direction. It's going to start pointing to the left as you go to the left. Does that make sense? The field switches direction. On the right is to this way, and then so because there's a positive charge here, it's pointing that it's going to push away positive charges and attract electrons to it. Right? So this is your charge. This is your field, and your electric potential. I think you know that because gradient of potential is equal to the electric field, that's in one dimension, that's just d over dx, right? And so the potential is really an integral of the electric field, right, with a negative sign. Potential is an integral, so you can pictorially integrate this, right? It's a constant. What's the integral of a constant? It's a linear function. So that much you know already, right? And so if I were to plot the potential, in fact, I can go 2 steps and just plot the conduction band energy, and that will be actually minus electron charge times the potential. That's how it will look, right? Conduction band as a function of space. Right? And so what I'm saying is, because there's a constant positive field here, when I integrate that, there'll be a linear change in the potential. Right? So the band will change linearly, not parabolically or not power law. It's linear. Right? And sometimes you get confused. What direction is it going up, going down? Here, you should just look at the charge. It's positive charge. The conduction band is going to bend so that the electrons pile up around there, right? So it's basically going to do like that. That's because if I release an electron in the conduction band, it should go towards the positive charge. Right? So that's the idea. So it's coming here. And similarly, if I release on the right side, it's going to come this way, and that's my conduction band as a function of x. Right? Where's the valence band? Valence band is always the band gap below the conduction band. Right? That's Eg. That's not changing, so the valence band is going to do that. Right? That's the energy band diagram. If I have a positive charge inserted, sorry, I have it somewhere down here. Yeah. This is the band diagram. Valence band, conduction band. So if you leave electrons here, as you can see, the electrons will kind of pile up here, and this can be, microscopically, it's called a triangular quantum well, and people have used this for some interesting devices as well. So this is a triangular quantum well. If you make it very deep, and you have these quantized levels and all that sort of thing. Meaning for electrons, this is the potential they're seeing in space. For holes, as you can see, it's interesting. If you create holes, they will not stay here, they will go away. They'll get pushed out, but the electrons stay there. So you can take that and then you can flip it around and say, well, instead of positive charge, I put negative charge. You can see everything will flip, and this will bend upwards now. If you have negative charge, it's going to trap holes. Right? So now, if you want to move across this sort of a region, you want to move electrons across. You see they'll get trapped. But holes, there'll be a big barrier for them. They will get reflected. Because for holes, this is a barrier. Do you see that? This is a hole barrier. And so this is how you create a barrier. You can put a positive charge and you can create a barrier for holes and that sort of thing. So now you can take the positive charge and create an equal and opposite negative charge here. It's a dipole now. You can create all these things. And I think you know that when you create a dipole, what will happen is, again by Gauss law, what will happen is the field, again, because of this, there will be a field, kind of like that here. Because of this, there will be a field that way. But if they're exactly equal and opposite, the fields will cancel outside the planes of dipole. Will cancel exactly. And what you'll be left with is just a field which is inside, and that field will be exactly sigma by epsilon. It's twice of that original field. You add it up. And when that happens, you can draw your energy band diagram, and your potential, I think you can see what's going to happen. Nothing happens outside here. So outside there, the bands remain flat. The bands remain flat. But the moment you get into that region, there is a large field that, if I release an electron here, it always wants to go to the left. You see that? Because it wants to go to the positive charge. It's getting, in some sense, hammered twice. It's getting pulled by that. It's getting repelled by that. Okay. So as a result, the band diagram will be, and the field is constant, so the potential still changes linearly. linear change. So the band diagram will look like that. Okay? The bands will bend. Does that make sense? We're just drawing pictorial representations of Poisson equation and nothing more than that really in some sense. But you can see you start building these blocks and say that clearly here, if I shoot electrons that way, this region is going to give it a kick. It's going to speed it up, right? Because it's just like rolling a ball down. You see, it's going to have a little bit of extra kick in the energy if you go that way, right? But if you try to push electrons this way, it's a very hard chance. It's a big barrier. So electrons will not like to flow that way. They will like to flow this way, right? And similarly, holes would love to flow that way because they get a kick as you go around. So this is a barrier. So you can see the directions in which they can flow easily and which is harder for them. And it looks, and what we'll show in the next class is this is an exponentially hard thing because the electrons that can make it here are the ones that have extra energy, and you have an exponential tail here. So the current goes down exponentially with this barrier height, exponentially. This is very important. Okay? And what is this barrier height? Maybe you can tell me, because the field is constant, the potential is always the area, is the integral of the field. Right? So the area under the curve is the potential, right? Barrier height. What is it? It's basically, the barrier height is just sigma over epsilon times the thickness of this dipole. Right? That's the barrier height. It's nothing more complicated than that. It's actually, this is it really. Now, these are sheet charges, but what's actually amazingly nice is a conservation law that if you, instead of a sheet charge, if you expand it and you make it, a constant volume charge, and you expand this one and make it a constant volume charge. So you see what I'm doing? I took a sheet charge, which is very sharply peaked, and I said, I'm not sharply peaked. I'm going to have the exact same amount of sheet charge, but I'm going to spread it out over a certain amount of volume now. Makes sense, right? What that will do is, as far as the fields go, I think you can see mathematically at least what's going to do. Because you're a sheet charge, you're at a sharp discontinuity. All you're doing, this thing is an integral of that. This thing is an integral of that. Right? So you can pictorially integrate now. I come in, there's nothing to integrate, and then I hit here, and there's a constant function now. So what will happen is the field is going to increase like that. Right? Because it's constant, the charge is constant, the field is linear. Right? And then you go to negative, it will come down. Does that make sense? So instead of what we had before, it's going to, the field will not be constant, it will be a triangle like that now. Right? And what will happen to the potential is you have a linear function, so the potential will change parabolically. Does it make sense? It will change. If this is function of x, you integrate it, you get x squared and some linear term as well. So it will change parabolically, and it will look, if I were to sketch it, it's going to look, something like that. And I think you will make the connection that this is exactly the picture of a p-n junction. That's what we did earlier. Why? Because the charge inside the p and n region at the junction is exactly this. You have, on the donor side, this is n side, this is p side. What you have here is you have a region where there were donors, but they were ionized because they found lower energy states there. The electrons went up there, and your holes that were ionized. So this was Q times the donor density. This is Q times the accepted density, and then this what happened. So this is a p-n junction, and then in a p-n junction in 3 dimensions, if you create a planar junction, this is how band diagrams will look. And what is very important is if I take a sheet charge and I, say that instead of sheet charge I have this, then out here, nothing changes. The field, the potential, all of them stay the same. It's only inside that things change. This is, I think you know that as a Gauss law, it's a moment theorem, that if I ask the question, well, I have a sheet charge of density sigma, what's the field here? Well, we calculated it is sigma by 2 epsilon. That's the field, right? Now I ask the question, I have the same charge, but I spread it out into a volume. What is the field here? The answer is the same. hasn't changed. Right? So outside it hasn't changed, but clearly it has changed here. So, yeah. Okay, so I think we are getting close to the end, and you can now kind of play with it and create all these other structures. You have flat bands when you have no doping. We just showed that if you dope it positive and negative, you get a hole barrier. You can get an electron barrier by flipping the direction of the charges. You can make triangulars and all this sort of thing. The next question I want to ask is something which is actually of a very fundamental importance now. Actually, let me think of it this way. Maybe it's better to do it in the next class. What I'll do though is for energy band diagrams, those of you who want to use it, there are a lot of tools that you can buy, but there are also very nice free tools available that you can use. Very, very nice free tools. And one of them runs on pretty much all computers, but it solves it in one dimension. So it's called a 1D Poisson equation solver, and we use it very heavily for semiconductor device design. And actually, those who are interested, I can link you up. I can give you the links where you can download and install. Here are some examples of structures. Here's a silicon PN junction diode, silicon with doping densities of acceptors and donors, 1e16. And then you ask, calculate me the band diagram, the charge, the field, all that stuff, and it will do it all for you. CV, capacitance voltage of a MOSFET structure or a quantum well structure. It will do all of that. You just define it and it will do it. And here's how it will look. So the outputs of it. Here's your band diagram that we just talked about. Conduction band, valence band, and Fermi level for a PN junction. Here's the charge. Very high electron density so hole density on the left, electron density on the right. And the electron density goes down exponentially as you go from the N side to the P side. So it will calculate all these details for you. Here's the electric field. This is flipped because the junction is in the other direction, but that's what we were trying to do here on the board. This is our field. What we could get analytically, it does it much more carefully. What it does is it solves Poisson equation, but at the same time, if I don't have a same semiconductor material all throughout, if I have things that happen here, for example, inside this material, I put a little quantum well, which is a narrow bandgap material. Let's say I can do that. In fact, that's a very useful device. It's a LED, light emitting diode structure. Put a quantum well. Now, Poisson equation doesn't know anything about quantum mechanics. Poisson is a classical physics, right? So you need to solve Schrodinger in parallel with Poisson equation. This is a self-consistent Schrodinger Poisson solver, and that's what this program does. It solves both Schrodinger and Poisson self-consistently, and as a result, it gives you details that are consistent with quantum mechanics at the same time. So, yeah. For example, if you take a diode, which is a metal insulator semiconductor structure, so you have metal, silicon dioxide, silicon. It's a MOSFET, MOS structure. Right? So it will calculate your energy band diagram. And here's the very wide band gap silicon dioxide. It's an insulator. Here's silicon, 1.1 eV band gap. And you have applied 4 volts on the gate metal. And the bands are bent. And we're going to discuss that in quite some detail in the next class about how does the charge here depend on the voltage you apply here. But it calculates the whole thing. You can see here, if you zoom in, there's a little triangular quantum well. That's where your inversion channel of a transistor forms. It's a 2D electron gas, and so there's some quantum aspect to it, and this program actually calculates all that stuff self-consistently. And okay, now how do I reduce the size of this thing? Oh, okay, good. And then you can plot, basically capacitance as a function of voltage, and then other things. Here's a quantum well, all these other details. So you can run that. Okay, so what I want to do is end the class today with another question, which will motivate the Schottky diodes and the PN junctions that we're going to cover later, specifically Schottky diodes to start with. So what we'll ask now is the following. Okay? I'm going to take 2 metal plates, large metal plates, and then I put an insulator in between them, okay? And metal and metal. And then I connect it to a battery and apply voltage, right? So it's a MIM capacitor. This is a capacitor, a parallel plate capacitor. The question I'm asking is, what is the charge? And I think you know, because I have planar plates, I'm really interested in what I can call as the sheet charge, sheet charge density. What is the sheet charge density or the charge on the metal plates as a function of voltage I apply? What's the answer to that? Right? So if I apply 1 volt across this, how much charge am I putting on the metal? What's the answer to that? Yeah. So there's no trick in that. It's a very simple capacitor. So what's the charge? Charge is, so there? That's right. So if you know the thickness, so essentially the answer is it is just the capacitance times voltage, right? And what is the capacitance? If you know the insulator material, let's say it has, let's call it a barrier. Right? Dielectric constant, the thickness of that is dB, let's say, right? And dielectric constant is epsilon b. Then the capacitance happens to be the dielectric constant over. There's nothing else. I mean, this is the answer to it, right? There'll be some details of fringing fields and all that. We're not bothering about that right now. So the charge density, you can write it, instead of writing it sigma, you can write it as Q times a sheet density of electrons in the metal. The metal can be very thick, but where will be those electrons? They will actually be on the surface, meaning electrons here and positive charges here. Make sense? Equal and opposite. If you draw the microscopic picture of it, what you have here is a let's say the voltage is positive here. What you have is a positive sheet charge here and a negative sheet charge there. And you can go back and make a connection to this picture. It's the same thing, no difference. Okay, so what the battery really does is taking, if I apply positive voltage here, all it's doing is moving charges around. It just takes a slice of electrons from here and puts it there. That's all it is. The whole thing is still charge neutral, right? It didn't do anything fancy. It just took some electrons from here, put it there to minimize the total energy. The electrons crowd up at this bottom interface, the positive charges, which are the ions of the metal on the top surface. And you have electric field in between them inside the dielectric, etc., right? Now, the question we're asking now is, I'm going to take this material, and instead of a metal, I'm going to replace it with a semiconductor. This is now a semiconductor. Okay. So now the question is, what is the charge as a function of voltage? And so the answer will not be very different. In fact, in semiconductor, they will have typically a work function and all that other things. There's a little difference. And you can write now that, let's call this CB. It will be V minus maybe some threshold voltage which is required to put charges in the semiconductor. This is what we generally use. And what we'll see in the next class is this is kind of correct, but it's actually not quite. There's a lot more complexity to this. And that's kind of the heart of many of these devices we are going to look at. So in other words, for a metal, what I'm saying is the charge changes linearly with the voltage, right? But the moment you put a semiconductor, we'll start with a two-dimensional semiconductor, like a moly sulfide or something, for example, and then you can go to silicon and others. We'll see that it will depend in a very strange way. It will, for a large window of charges, large window of voltages, is going to depend exponentially. The charge will depend exponentially on the voltage. And for another window of voltages, it will depend as a polynomial. So the plot will look like this. If you plot a log scale of the charge in the semiconductor now as a function of the voltage, it will look exponential. If I plot log of that, and then it will become saturated. That's what we're going to see. Right? And this is actually the heart of a transistor and many other devices, PN junction, Schottky diodes. This exponential here we'll see will be close to what you call the 60 millivolt per decade. This is what it's going to look like. So it takes 60 millivolts to change the carrier density by a factor of 10. And the moment you reach here, it will look some power law, as in other words, let me just write down this and we end here. Okay. Sheet density for very small voltages, we'll call some sort of a threshold voltage here, VT. You go very lower than that threshold, the sheet density will look like this. There'll be some constant, it's a quantum carrier density, times e to the power Vg, V over V, thermal voltage. It will depend exponentially. So in a log scale, it looks linear. Out here, it will depend as V to the power some 3/2 or 1/2, I forget exactly. So this is the heart of a MOSFET as well. This is the off state of a transistor. This is the on state of a transistor. It's basically a capacitor which you're controlling. You slap on other electrodes and you flow current, but the gate controls completely how much charge there is. So that's a transistor on and off and all that sort of thing. But also, this is also a PN junction picture. It's also a Schottky diode. All of it boils down to this. And the answer to that is in this question. What is the charge as a function of voltage? And what we'll see in the next class we derive, the answer is not as simple as that. There's a lot more complexity. But, so we will actually derive that whole thing. We'll derive an expression for this. And then from there, we can go and do a lot of other things. That answer is not quite right. You can see right away that if you apply a negative voltage, this is a sheet density, this term can become negative, but the sheet density